Welcome to lecture 13 of EC 3030. So in this lecture we will be continuing our discussion on PN junction, which we started in the previous lecture, lecture 12. So topics that will be covered today are included in section 6.1.1 and section 5.1.3 in the textbook by Pire. All right, so PN junctions, we have already said why PN junctions are important. This is the basis for most of the semiconductor devices, if not all. So the basic structure is like this. On one side we have the p-type semiconductor and the n-type semiconductor. Now in the p-type semiconductor, what we are showing here is a dopant atom. So the negative dopant atom which is an acceptor. So the negative sign represents the nucleus, the charge in the nucleus, which compensates the positive charge of the hole of the acceptor atom. So this is an abstraction of the acceptor atom. All right, and on the n side on the right, we have again these circles represent the donor atoms. So the plus sign represents the positive charge in the nucleus, which compensates the negative charge of the electron, which participates in which this donor atom can give. All right. So now we will try to understand what happens when we put a p-type and n-type material in contact. Now what will happen is that if you put them in contact, the holes from the p side will go towards the n side and the electrons from the n side will go towards the p side, and they will meet each other and recombine or annihilate each other. Now why does this movement occur? The reason can be explained by a very simple analogy. For example, if you have a container and you introduce two different liquids, for example, one liquid is color red, another one is blue, and you introduce these two liquids from the two sides, and you have a barrier in between them, and when you lift the barrier, you will see that of course what will happen is that the red and blue liquids will the red will move towards the blue and the blue will move towards the red, and they will mix. So this is called diffusion, and what is happening here is actually diffusion, because in the p side you have a higher concentration of holes, which are so on the other hand in the n side you have a lower concentration of holes, so the holes will move from higher concentration to lower concentration regions, and same for the electrons from the n side to the p side. And as they move, as they diffuse, they just recombine and cancel each other. So what happens is that once they cancel each other, you will have a space charge region which is negative in sign, negative in charge in the p side, and a space charge region which is positively charged on the n side. Now this will continue for a certain amount of time, this movement and creation of this depletion region. So anyway, so we will have in a PN junction, when we put a p-type semiconductor and n-type semiconductor, there will be a depletion region at the interface between these two differently doped regions, and this is the depletion region. Okay. So now what we want to look at is how the band diagram of the semiconductor or the PN junction look like as a function of the position. Now what we want to plot is how the position of EC and EV and the Fermi level looks like as you go from the p-type semiconductor towards the n-type semiconductor region. All right. So here what you have here is the conduction band, edge of the p side, and the valence band, edge for the p side here on the left, and the same for the n side on the right. Okay. So one of the most important rules for drawing the band diagram is that at equilibrium, the Fermi levels for all the regions will line up, meaning that in this particular case what we are showing here is that the P region, the Fermi level and the N region are not lined up. We will line them up, but before that let's note that on the P side, as we have said, P side the Fermi level will be closer to the valence band, and the N side the Fermi level will be closer to the conduction band. Alright, so now what we have to do is we have to line these Fermi levels up, line them up. And how can we do that? What we can do is that, because these are energies, these are relative, so we can just fix one side and move the other side, the energy levels, and if we do that, this is what will happen. So we have, in this case, the left side, the energies in the P side, we have moved them up such that the Fermi levels of the N side and P side line up. Alright, so the same curve here, the same plot here. Now after we have lined them up, what you can see is that now the conduction band in the P type semiconductor is at a higher energy than that of the N type semiconductor, and we have to connect these energies. So what we do is that we connect them like this, and the valence band, we do the same for this. Now this connection has the fact that we connected the EC of the N side with the P side and the EV of the P side with the N side as a significance, and the significance is that whenever there is an energy, so this is what we call the band bending of the conduction band or the valence band, and what it signifies is that whenever there is a band bending, there will be a certain depletion region, and the depletion region covers the region where the band bending occurs. So if we draw the band bending properly here, then we see that the band bending is happening in this region between this and more like this, both same for the band bending for conduction band, valence band. So the depletion region for this particular case will look something like this. So the depletion width in the P type semiconductor is like this, and the N type semiconductor will look like this. So we will not talk a lot about the depletion width and the quantitative features of the depletion, but most important thing to remember is that the depletion width or the depletion region corresponds to the region where the band bending occurs. Alright. So now let's look at the different current components in a PN junction, and for this case we will consider the current components at V equals to 0, basically when the EF and when the N side and P side line up in this case. Alright, so when we talked about the fundamentals of semiconductors, what we have shown is that what we have considered was that if we plot the carrier densities, then in a p-type semiconductor the carrier density for the electrons will be very small, so the y-axis here is n. So this is the amount of, so this, what this curve shows is the amount of electrons or the density of electrons per unit energy per unit volume. Alright, now this is the p-type semiconductor, so the amount of holes, the number of holes per unit energy per unit volume will look like this. Now this is much more larger than what we have here. So let's say this is NP electrons in the p side and this is PP number of holes in a p side. All right, and if we integrate this curve, this will come out to be Ni squared over Na, and if you integrate this PP curve, so this will come out to be Na, the area under this curve. All right. Now what we can, okay, so again similarly for the N side you have a lot more electrons, so it will look something like this. Nn number of electrons in the N side per unit area per unit volume will look like this, and Pn will look something like this, very small. Okay, and this is area under this curve is Nd, and the area under this curve is Ni squared over Nd. All right. Now let's look at the different current components. So here what we can say is that, okay, so there are a small, so this is p-type p-doped, so there will be a very small number of electrons here, and these electrons will flow from the N side to the p side. So we call this current density Jn moving from N side to the p side. All right. So this is the first component of current which flows from N side to p side, simply because there is this barrier and N side has a lower energy for the electrons, so this will try to move that side. All right, so now here on the N side, okay, so this was actually wrong. This should have been called Jn moving from p side to N side. All right. Now on the other hand, in the N side you have a lot of electrons. So you have a lot of electrons. Now as you go higher in the energy, the number of electrons will decrease. Now what is happening is that because these electrons are here, these electrons will try to cross the barrier, but it will not be able to pass. So these electrons try to move from the N side to p side, but because there is a barrier they cannot move. But there is a certain number of electrons that have enough energy to cross the barrier, and these electrons cause a current, and that current is flowing. So that current creates an electron flow which flows from N side to the p side. All right, so actually this current should actually flow this way because it's electrons, and this current should flow in the opposite direction to the electron flow. All right, now let's consider the case for holes. Now one thing to understand is that for holes, going in this direction actually lowers the energy, meaning that for holes so from top to bottom is the direction where the energy increases. In other words, it means that holes in the p side has a lower energy than holes in the N side. So when you have a lot of holes here, and these holes actually see a barrier going from p side to n side. So these holes will be reflected, and these holes, the holes that have higher energy, will be able to pass. So we call the current due to the holes that are moving from the p side to the n side. On the other hand, similarly, because it's on the top of the barrier, there will be some holes that will be moving from the n side to the p side, and that is what we called Jp, moving from n side to p side. Okay, so these are the different current components we have. So from semiconductors, electrons, from the p-type semiconductor, electrons move from p to n, and then you have in the n side, you have electrons that are moving from the n side to the p side, and similarly for the p side, similarly for the holes. Now at equilibrium, what happens is that because you don't have any voltage applied across the p-n junction, so by definition there should not be any current flowing through the system, and the way it's balanced out is this, that Jn p to n is equal to Jn n to p. Basically the current that the electrons move from n side to p side is equal to the number of electrons that move from p side to n side, and similarly for the holes, Jp p to n equals Jp n to p. So this essentially ensures that the current, there is no current that flows when you don't have any voltage applied across the p-n junction. Now the description that we have given here is actually very simple, and there is not much insight that you can gain from this discussion, but it will important when we discuss the current that flows in the p-n junction when you apply a voltage across it, and this helps us to distinguish, understand the difference between the forward bias and the reverse bias. Alright, so now let's try to understand what happens when you apply a positive voltage to the p-type semiconductors. So basically the forward bias, where you have the p-type semiconductor and a higher voltage than the n-type semiconductor. Alright, so this is the case for a p-n junction with a zero applied voltage, and this is the depletion region here. Now if we apply a voltage, positive voltage, then what happens is that the region of depletion decreases. So the depletion will decrease, and also what will happen is that now the p-type semiconductor will inject some majority carriers of this side, inject some holes into the n-type semiconductor, and the n-type region will inject some electrons in the p-type region. And what will happen is that at the edge of the depletion region, there will be some, on the n side, edge of the depletion of the n side, there will be some excess holes, and at the edge of the depletion of the p-type semiconductor, there will be some excess electrons, and these electrons and holes will create a current in the p-n junction. All right, so in forward bias, what happens to the current? That's the next question. So as we have seen in one of the previous slides, the electron density as a number of electrons at a given energy decreases as you go higher in the energy, right? Now what is interesting is that, so this dotted curve again is for v equals to 0, and the solid curve is for v larger than 0. Now what you can clearly see is that for the electrons, now in the p side, on the n side, the barrier has gone down. So as a result, you can have more electrons that go from the n side to the p side. This is essentially saying that the n side is now injecting electrons to the p side, and the reason it is injecting more electrons to the p side, and the reason is possible is because the barrier for electrons to move from the n side to p side has now reduced with a positive voltage applied at the p side, or with a positive with a forward bias. So what we can write is that Jn, and the electron is going from the n side to the p side at a given voltage is equal to Jn at n to p. Now we say that this is at v equals to 0, and this actually increases exponentially. It's a function of kt, and the reason it increases exponentially is because the amount of carriers that can move here from the left to right follows an exponential relationship with the barrier height, and the barrier reducing by an amount qv actually creates increases the current due to the electrons flowing from the n side to the p side to increase exponentially. All right, but now what happens to the current that was due to electrons flowing from the p side to the n side? And what is interesting is that this current actually does not change that much. So this current remains the same. So Jn, where the electrons are flowing from the p side to the n side at the voltage V, is actually Jn p going p to n equals to 0. So almost equal to that. And why is that? The reason to understand that, we can draw a very simple analogy. For example, consider a waterfall like this. And what you can immediately realize is that the amount of water that will flow or fall in this waterfall does not really depend on the height of the waterfall. So if the waterfall is the depth or the height of the two sides of the waterfall is larger, the amount of current, the amount of water that will fall will also be same if the waterfall is rather shallow. So this is actually a similar thing that is happening here. So the electrons that is flowing from the p side to the n side actually does not depend on the voltage. So again, the n side is injecting the amount of electrons that the n side injects into the p side increases exponentially with voltage, and as a result the current also that the n side injects in the form of electrons to the p side also increases exponentially with a forward bias. And the case is also the same for holes. So for the hole, so the current due to the holes moving from n side to the p side at a given voltage V remains the same. On the other hand, the current due to the holes moving from the p side to the n side at a voltage V is equal to the same current at V equals to 0 multiplied with QV by KT. So finally what we can write is this, that the total current J is Jn between minus Jn p to n. All right. So here the n to p or p to n actually represents the direction of the electron flow, not the current flow. And here it's this p to n and n to p represents the direction of the flow of the hole. All right. And if you do this, so what we'll essentially find is that this current becomes proportional to qv by kt minus 1, and we say that the constant exponent J naught. Okay, so now let's look at how the band diagram changes as you apply a forward bias across the PN junction. So this is the PN junction, that band diagram of the PN junction with a 0 applied voltage and at equilibrium. And so as we have said is that at equilibrium the Fermi levels will line up, meaning that EFP will be equal to EFN. Now if we can say it in a different way as well. So we can say that EFP minus EFN equal to minus QV. So what it says is that the difference between the Fermi level of the two sides will be equal to negative of the voltage applied multiplied with the charge of an electron, and in this case V equals to 0. So we get EFP minus EFN equals to 0. Okay, so now we have applied a voltage larger than 0, basically a forward bias, and what we see is that there has been the Fermi levels of the two sides are no longer lined up. There is a gap between them, and as we have said in the previous slide, we have said that EFP minus EFN equals minus of QV, and basically this gap between EFN and EFP is QV. All right, so again if we compare between the previous the band diagram, the previous slide and this one, what you will see is that we have kept the bands or the energies on the n side the same position and just moved the bands or the energies on the p side down by amount of QV. All right, so in the next slide that's what we will see. So the dotted curve is the energy band diagram when V equals to 0, equilibrium case, and the solid line is the one where V is larger than 0. And what we can see is that in this case the energy levels at the n side are constant, just that we have moved the energies on the p side by an amount QV. So this gap between the EVs or QV, and so this is the EF, and this black dotted curve is the old EV, and this is also equal to QV. All right. So now let's look at what happens in the reverse biased. In the reverse biased, the p-type region is a lower voltage than the n-type semiconductor. So if we first start with an equilibrium condition of a PN junction, voltage V equals to 0, and this is the depletion region. Now if we apply voltage a negative, so this should have been reverse bias. So now we have a voltage that is negative at the p side, and what will happen is that the region of depletion will increase. So the depletion region will become bigger as you apply a negative voltage in the reverse bias. Alright, so now what happens to the band diagram? So again, this is the band diagram at equilibrium, and at equilibrium we have the Fermi level at the n side and the p side at the same value. In other words, they are lined up, and then we have said that EFP minus EFN should be equal to minus QV, and this is 0. Alright, but now when you apply a negative voltage at the p-type semiconductor, the band change such that EFP and EFN are no longer lined up, and if we write down the equation, so equation looks like this: EFP minus EFN equals to minus QV. So V is negative, so EFP, the Fermi level of the p side, will actually be higher than that of the n side, and this gap here is Q, the multiplied with the magnitude of V. Alright, second, what we have done is that we have kept the energy of the n side constant at the same position, and then moved the energy levels in the p side up by QV amount. So just so we can compare, so here the dotted curve is for V equals to 0, and this curve is for V equals smaller than 0, and this difference between the conduction bands for these two cases is QV, and this difference here between the Fermi levels is also QV, and this gap is also QV. Alright, so now what we can see is that if we are at the n-type semiconductor region here, the electrons will now see a larger barrier, and as a result what will happen is that this the current that flows due to the electrons going from n side to p side will now decrease by a factor of QV by KT. Now V is negative here, and as a result this will be e power QV minus over KT smaller than the value for V equals to 0, and if this voltage V is, the magnitude of V is larger than 3 times KT by Q, then this actually will become almost 0. So if the voltage is smaller than 3 KT by Q, then the current that the n side injects to the p side will be almost 0. On the other hand, what we have seen in the case when we are discussing forward bias is that this the current due to the electrons flowing from the p side to the n side is independent of the barrier height. So this quantity Jn due to carriers moving from p to n will remain almost the same, independent of V. It will remain the same. And similarly for this case, the current carried by the holes due to the holes moving from n side to p side will almost remain constant, independent of V, whereas the current that flows due to the holes moving from the p side to the n side will be almost 0 as long as voltage is negative kT by Q. So if I plot the current voltage characteristics here, so as long as this voltage is smaller than kT by Q, what will happen is that this value will saturate at a certain voltage, and that voltage of saturation will be just be equal to the sum of this and this here. And as the voltage, so we call it minus I naught or J. Okay, so let's plot J, the current density. So this will be J naught here, and then it will, this curve will pass through 0, and so this is the reverse biased, and in the forward bias it will just follow an exponential dependence, and this is the forward bias which we discussed in one of the earlier lectures.